Uh, Hello, friends. Hello, everyone. I hope you are all doing fine and you are all healthy and well. Friends, I am myself. I am Manish Rathod. I am presently posted as Deputy Director in Narmada Control Authority, and I'll be taking a lecture on Introduction to Hydropower Plants. I will start with a brief introduction of myself. I did my BE from SGS ITS Indore and then did MTech in structures from IIT Bombay and then joined Central Water Commission as Assistant Director in CWC headquarters. I worked there for a period of 5 years in Hydel Civil Design Directorate, where I dealt with the design of hydropower plants, especially which are in the northeastern part of India, including the projects in Bhutan. Uh, Thereafter, on promotion, I was posted to National Water Academy, where I worked as the core faculty of um, of NWA for a period of 5 years. And from last 1 year, I'm here working in Narmada Control Authority as Deputy Director. So this is it. This is about my introduction. I will now start with my presentation. I'm going to share my screen. I hope you will be seeing this. So, so friends, my lecture, as I said, will be on an introduction to hydropower plants, where I'll be talking about different components, their functions, and briefly touch upon the design aspects of the design aspects and design fundamentals of different components. I'll not go deep into the design, but yes, we will touch how it is designed and why it is designed that way. This is what I'm going to discuss. So friends, if we talk about the types of hydropower projects, there are basically different types of project based on the purpose, based on the storage and so on. So if you first classification, if you see, it is based on the purpose, whether it is an hydroelectric project, which is purely used for hydropower generation, or is it a multi-purpose project? Generally, the projects whenever it is designed, except for run-of-the-river scheme, generally the projects which are storage type of projects, they are generally multi-purpose. Because if you are going to create a reservoir, you will be using it for not only for hydropower generation, but also for domestic water supply, industrial water supply, irrigation, and so on. So basically, the project which is used for more than one purpose is called as multi-purpose project. Hydroelectric project is purely a hydropower project. Then based on the type of storage, there are two kind of projects. One is the run of the river scheme or run of the river project, which is basically, in these run of the river projects, we have a very small storage. We cater only for the daily fluctuation of the incoming water. So the storage is small, and when the load on the grid is small, the level of reservoir goes up because the outfall is less than the incoming water. And when the load is high in the grid, the water level will go down because the demand is more than the water which is coming inside, demand of power. So generally in the morning time from 8 to 10 or 11 or so, the power demand is more. And in the evening time, during maybe from 5 to evening 8 o'clock or 10 p.m., the demand is high. Rest of the day in the afternoon and in the night time, demand is generally low. So run of the river scheme generally take care of these kind of peaking. On the other hand, we have storage projects. Storage projects are basically, they have very large storage. They are not catering only for the daily demand, but they are catering for the yearly fluctuation of demand and water inflow. You see, we have monsoon for a very small amount of time. So most of the rivers, they are not having constant and large flow throughout the year. They are having these rivers are having more flow during the monsoon period and having a very lean small amount of flow in the only which is contributed by the base flow during the non-monsoon period. So we need to create a large reservoir, which is basically the storage which stores the water for during the monsoon time, and it will then use that water during the non-monsoon time. So this is called storage project. And uh, as compared to run of the river, there are some differences that we will be discussing. What are the difference between storage and run of the river, and how the operation is different, how the storage is different, how the layout is different. All these three things are different in these cases. So then come normal operation versus pump storage. Normal in generally in case of normal operation, we have an upstream reservoir. The water comes from upstream to downstream and generates electricity. But in case of pump storage, this kind of different kind of turbines are used. These turbines are called as reversible turbine. In these reversible turbine, what we have is when we have the low power demand, sorry, when we have the high power demand, we take the water from upper reservoir to down lower reservoir. We have two reservoirs in case of pump storage schemes. We take water from upper store reservoir to the lower reservoir and we generate electricity. But when there is demand is less but supply is more, means like thermal power plants, they cannot be stopped in a very small amount of time. So generally, if a 1,000 megawatt thermal power plant is there, it will keep on generating 1,000 megawatts. So what will happen if the demand is less and the supply is more? In that case, what we do is, instead of wasting that energy, we will use that energy to pump that water from lower reservoir to the upper reservoir. And then it's a kind of battery. To store the electricity, we cannot store AC power. The batteries are very costly and difficult to maintain and have a very small shelf life. So that's why we take that excess power and we use that to pump the water from lower reservoir to another upper reservoir. And during peak demand, again when there is a more demand and less supply of power, we use the water on the upper reservoir, generate electricity, put it back into the lower reservoir. This is how the pump storage schemes work. So if we talk about the different components of a hydropower project, starting from the intake to the outfall of the water. uh, Intake means where the water is taken into the system of a hydropower project, and outfall is where it is given back to the river. So if we talk about the components, the first one is the diversion structure, which can be a dam, which can be a weir, it can be a barrage, whatever. It will basically, what it will do is it will divert the water from river into the intake. It will actually increase the water level inside in the river, and then that water is diverted into the system. So that is a diversion structure. It can be dam, it can be weir, it can be barrage, it can be any kind of structure which is a kind of blockage in the river, which uplifts the water level and creates a pool of water. The second is the intake structure. It is the inlet of water. The water which enters the system enters through the intake. So at an intake, we have a kind of beam column type of structure with trash racks, with bell mouth shape, with gates and everything. That entire arrangement is called as a intake structure. Next, we have desilting arrangement. In this desilting arrangement, it is generally provided in cases where the silt is more. The quantity of silt which is present in the river is more, maybe because the catchment has less forest, or the soil erodes much from the catchment, or any kind of reason. Wherever in the river you have large amount of silt, it has to be removed from the water before generating power. There are two reasons for that. The first reason is the silt has to be given back to the river, otherwise scoring will take place. The water which from which the silt has been removed causes scoring in the downstream. So that silt has to be given back to the river system, otherwise to prevent the scoring. Number one. Number two is that if silt is more in the water, then what will happen? Higher content of silt will actually erode the turbine blades and all the structures which are coming in the way, especially turbine blades and the governors and the spiders and everything which is coming in its way. So to prevent that erosion, we need some sort of arrangement which can remove the silt from water and result in a clearer water. That is called as desilting arrangement. If it is underground, it is called as desilting chamber. If it is on the top, it is called as desilting basin. The next component is power channel or headrest tunnel. One thing I forgot to tell is that desilting arrangement is not always necessary. If the water in the at the point of intake is clear enough, you don't actually need a desilting arrangement. Especially in case of storage projects, the length of reservoir is more. If the length of reservoir is more, all the silt is settled in the upstream part of the reservoir. So at the downstream part where you are taking the intake, generally you don't have any silt. You already have a clear water. So you don't need a desilting arrangement. Next is the power channel or HRT or headrest tunnel or HRC, whatever you can call. If it is on the surface, it is called as a channel. If it is underground, it is called as a tunnel. In a power channel or power tunnel or headrest tunnel is a component that takes water from the intake or from desilting chamber all the way to the turbines. All right. These are the components that I'm talking about generally for a run of the river scheme, not for a storage scheme. For a storage scheme, some component will be removed from this list. So this is a tunnel that takes water all the way to the turbine. In between, if the length of this power channel or headrest tunnel is large, then the water hammer effects will be larger. The pressure surge due to water hammer and surge will be larger, and that will result in a, if you try to design the entire tunnel for that larger pressure head, internal pressure, the thickness of lining will increase, and that may make your project uneconomical. So we have to provide a kind of surge suppressor or surge shaft or forebay, which is used to capture those water hammer effects. Okay, so this is a kind of capacitor. It takes the energy of water during water hammer and releases it back slowly. This is a surge shaft or forebay. It is provided at the end of the headrest tunnel or power channel. Forebay is on the surface and surge shaft is the for underground. Pressure shaft or penstock. Uh, after the water reaches surge shaft, it is taken to the turbine through pressure shaft or penstock. If it is on the surface, it is called as penstock. If it is underground, then it is called as pressure shaft. So that pressure shaft is generally designed for high internal pressure, and that is why generally it is steel lined. Generally, not always. If you can design RCC or if you can design PCC, you can go ahead. But yes, generally pressure shaft is given in case of high pressure drops, and in case of high internal pressure, you generally go for steel lining. Then comes the powerhouse complex. It contains all the arrangements for generating power, like the powerhouse that holds all the machines and turbines and governors and control units and everything. Then you may have a transformer cabin that or a GIS switchyard or GIS hall kind of thing. Okay, or transformers also. So that is a transformer hall. And if the TRT, the tail race tunnel, after this turbine is long enough, you may also have a downstream surge gallery in the powerhouse complex. That is a powerhouse complex. And finally, the tail race system that may be on surface or maybe underground. If it is underground, then it is called as tail race tunnel. If it is on surface, it is called as tail race channel. This is a typical layout of a run of the river scheme. So this is here. You have the on the left side you can see the dam complex. On the right side you can see the powerhouse complex. So let me just. This is a dam complex, and this is the powerhouse complex. If you see a zoom out, if you see a dam complex, can you see the dam is here? Dam itself is generally very big structure. And can you see in this layout, this entire layout, this dam is looking like a very small thing. Okay. Here is a upstream coffer dam. Here is a lower downstream coffer dam. Here is the main dam body. This is the diversion structure. Then you have the intake tunnels. Then you have desilting chamber. Then you have the HRT, manifold and hydrous tunnel. And one more tunnel is going on this way. It is the silt flushing tunnel. It takes the water from silt and gives it back to the river. In powerhouse complex, if you can see, you have this surge shaft. This HRT is coming to the surge shaft. Then we have pressure shaft, and then we have the uh, powerhouse and transformer hall and everything. And then you have a a tail race tunnel. So an image is worth 1,000 words, and a video is worth 1,000 images. So I'll show you the 3D views of how a hydropower project looks. I'll be showing two complexes, the dam complex and the powerhouse complex. These are the complexes that these are the powerhouse and dam complex of the project that I was involved during the design of during my tenure in Delhi headquarters. So first I'll show you the dam complex, how it looks, what are the different components. If you see, this is the dam, this is the dam body, these are the intakes, and somewhere in the downstream of these intakes there will be a coffer dam, and this tunnel is the construction tunnel. So to dig these tunnels and to excavate these tunnels, you need a access tunnel. But this access tunnel is this access tunnel to excavate these two tunnels. And once we reach this point, we go on this direction, left and right, both directions. So you get two faces to work on simultaneously. These are the diversion tunnels. These are the portals. And if you see this part, this green color part is the intake. It's a video. I can't zoom here, but if you are able to see, there are beams, and there are columns, and there are trash racks. And after that, there is a bell mouth, and these tunnels go to the desilting chamber. These tunnels are called as intake tunnels. These are intake tunnels, and these intake tunnels actually meet the desilting chamber. And this brown color tunnel, this is the excavation tunnel for the access tunnel for the desilting chamber. To construct these desilting chamber, you need access. You need the bulldozers to go in, the boomers to go in, and also to the trucks to take out that muck from the excavation site. So these are the construction tunnels, and you can see there are two tunnels going, one at the top and one at the bottom, because the construction goes on at two different fronts, and once you reach the bottom, it's impossible for the trucks to go to the top tunnel. So that's why you need two tunnels, one at the top and one at the bottom. Excavation starts from top and then comes down. When it reaches the bottom, the trucks will go out from the bottom tunnel. Then you can see these HRT manifolds. Manifold is only a kind of junction for the HRT, junction of HRT with the desilting chamber. So these tunnels are then meeting here, and clear water is taken from the top of the desilting chamber to the HRT, and the dirty water containing a very high amount of silt comes down from the bottom of the desilting basin and meets this blue color tunnel. This is the self-flushing tunnel, and this red color tunnel, what is this? This tunnel is actually a gate operation tunnel. There are gates which are installed at the end of the silt tunnels, start of the self-flushing tunnel. These gates are operated from this tunnel. This is called as gate operating gallery. And then from the silt flushing tunnel, the water is given back to the river. And this is the end of the diversion arrangement. Everything is clear. Now the manifold of the HRT and manifold of the SFT, self flushing tunnel, are I think clear. Okay. This tunnel is going in this way because to construct these self-flushing tunnels. Now I'll be showing another 3D view of the powerhouse complex. The HRT goes from the end of the desilting chamber to the surge tank. Now, how it looks? It looks like this. Here is the HRT which is coming and meeting the surge shaft. This is the added to surge shaft, means the access tunnel to the surge shaft top. And since it was an underground surge shaft, in this case it was an underground surge shaft. That's why we had a dome at the top of the surge shaft. And from the bottom of the surge shaft, you have two smaller diameter tunnels. These are called as pressure shafts. And this large tunnel is the HRT. It operates in the low pressure, and that's why it is concrete lined. And these pressure shafts, they operate under higher pressure. That's why it is these. That's why these are steel lined. And then you have two chambers, butterfly wall chamber and ferulation chamber. Butterfly wall chamber is used to install two butterfly valves immediately after the surge tank. Although there are two lock gates, stop lock gates at the start of this pressure shaft, but to get a precise control over the discharge and to cut off the discharge for maintenance purpose in the powerhouse, you have to provide, we generally provide the butterfly walls, and these butterfly walls are installed inside the butterfly wall chamber. Then these are all the construction and access tunnels. Then there is a vertical drop in the pressure shaft. So all the head is generated in the pressure shaft in this vertical part. Most of the entire HRT is almost horizontal, very small slope, 1 in 500, 1 in 1000 or so. But all the pressure is created in the pressure shaft. All the vertical drop is created in the pressure shaft. And then there is a pressure shaft manifold, and these two pipes are then bifurcated two times to create six pipes, six tunnels, six pressure shafts, which go and meet the machines. Before going to the machine, there is also again a wall that also is a butterfly wall that is called as a main inlet wall, MIV. And then it meets the powerhouse cavern. And then once the power is generated, then the water comes out from the draft tubes, goes into the downstream surge chamber. Why it was required? Downstream surge chamber was required because the TRT length was more. And then there is a big network of tunnels. Some of them are construction tunnels, some of them are access tunnels, some of them are temporary tunnels for drainage, some of them are only for taking some specific part like for example only for gantry or only for maybe bifurcation piece or so, which are created here. And if you see in 3D, these in plan it is very difficult to visualize that which tunnel is on top of which tunnel, but in 3D you can see it very easily. This entire video was made in using AutoCAD, and this entire 3D drawing also was made in AutoCAD. This green color tunnel is the access tunnel to downstream surge tank, because you need some access there also, but plus there should the top of the water level at the downstream surge chamber should be at atmospheric pressure. That's why you need a access tunnel. And then addict to construction edit tunnel and addict to main access tunnel, and then there are access tunnels, and then the drainage galleries, and finally out of these downstream surge chamber you have a tail race tunnel. This blue color tunnel is the tail race tunnel which goes back into the river. This is a typical layout. Of course every project is unique and all projects have different layouts, but yes, this is overall, I would say, an overall uh, layout of a run of the river scheme. The layouts will never be same, but mostly components will remain same, and their positions with respect to each other will also remain same. Although their dimensions can vary, their orientations can vary, their sizes can vary, and so on. Let's talk about important terms that you should know whenever you are discussing hydropower plants. First is the design head. Design head is the difference between the water level at the upstream and the tail race for which you are designing the hydropower project. Okay. Designing means you will design for maximum upstream upstream reservoir water level means FRL and the tail race normal tail race. This will be your design head. Gross head is different. Gross head means the difference between design head also has a component of head loss. You have to subtract the head loss. Head loss means the losses due to friction which are happening in the water conductor system. In design head, you have to subtract these head losses. Gross head means the difference, pure difference between the upstream uh, water level and the tail race means the FRL minus FRL whatever is the level in the reservoir minus the tail race level. All right. And net head means this difference minus the head loss. That will be the net head. Okay. The head at which the turbine will operate to give the best overall efficiency under various operating conditions are the is the design head. FRL minus the tail water level. Gross head is the difference between the elevations of water surfaces of the dam, reservoir, and the tail race under a specific condition. It's not necessarily FRL or MDDL. It can be in between also. Net head is gross head minus the head loss. Live storage, firm power, firm energy. Live storage is the storage in the reservoir which is available for power generation. Okay, so in a reservoir we keep some provision for the sill to deposit. That is called as dead storage. So an MDDL is something below which we never allow the water level to go. FRL से ऊपर नहीं जाता, but we do go up to MWL. But yes, live storage will be the storage or water volume available between FRL and MDDL, because you can never go below MDDL and you will prefer not to go above FRL. So that is called as a live storage. MWL is achieved only for a small amount of time. It cannot be persistent for a long amount of time. Firm power is the continuous power output in an entire period of hydrological at 90% dependability. 90% dependability means this much power will be available at least 90% of times. Out of 100 days, 90 days you will be able to provide this much of power. Okay, that is called as firm power. That is dependability. And firm energy is the energy which is corresponding to the firm power. So take this firm power, for example, firm power is 2000 megawatts, multiplied with time, you will get the firm energy. So let us discuss a little about the intakes. What are its roles, what are its components, and what are the design aspects. So the first role of this intake, it's very, I would say it's a very small component, but very important because it prevents the entry of trash in the system, in the water conductor system. Trash is very damaging because that will cause blockage, that will cause cavitation, not cavitation, erosion of turbines and so on. But more importantly, it can cause blockage because you may have small openings at turbines or in the spiders or in the governors, and there these small openings can be blocked by floating debris. So this trash rack actually will prevent, these intake structure will prevent the entry of these floating. Uh, this trash rack is used to prevent the entry of floating debris inside the system. Well mouth opening. See, there is a intake of water. The water at rest is coming into the in motion. So you have to provide a smooth interface between still water and the running water. So that's why you have to provide a kind of um, bell mouth opening, means elliptical shape opening, which will ensure the smooth flow of water, a laminar flow of water. it will ensure, this bell mouth opening will ensure laminar flow of water. Then transition is there. It is very difficult to construct a circular bell mouth. So generally we provide a rectangular bell mouth. The opening of the intake is rectangular, and then gate are also rectangular. So you have to provide rectangular. Generally it is preferred. And then, but tunnel is circular. So you have to provide a transition between rectangle and circle. So again, that transition has to be smooth. Otherwise it will cause turbulence in water. So transition is also a part of intake. And yes, we do have to provide the gates. So we provide gate shaft with air vent. Air vent is used to remove the air from the water conductor system when the gates are closed, when the water is full in the tunnel. So intake is an arrangement to divert water from the reservoir to the water conductor system. The objectives are the intake are to prevent the entry of trash, debris and other floating objects. Uh, the trash track does this job. To prevent and reduce the silt when the water is required for power generation, okay, which is likely to damage the runner. So to reduce the silt, what we can do is we can put this intake strategically at such a place where the generally the silt is low. Okay, so intake की location पे depend करेगा. It will depend on the location of the intake that how much silt will go inside the system, and also on the height of the system, height of the intake from MDDL, how high it is, from dead storage level, how high the intake is placed. That will ensure that small amount or as small as possible amount of silt is coming into the system. And to ensure the smooth hydraulic conditions means the flow should be laminar as far as possible. It is ensured by providing a bell mouth shape with elliptical profile, and to of course reduce the hydraulic height loss. Intake parameters, if you are going to design the intake, you will have to design two things. The first is what should be the shape and size of intake, and where you are going to place it, means the location of it. So the shape should follow a profile of the jet which is entering the opening. Generally it is an ellipse, okay, a quarter of ellipse. So it should be a smooth elliptical shape if you cut a cross section of the intake. Shape of the bell mouth is generally rectangular. There are again, as I said, there are two reasons. First is the gate itself is rectangular, so it is better to provide an rectangular bell mouth. Number two, it is difficult to construct a circular ellipse, circular bell mouth. It is easier to construct a rectangular bell mouth. That's why generally the shape is kept as rectangular, but it is not always the case. There are some projects, there are many projects where the bell mouth itself is circular. The size is set to keep the entry velocity to 0.6 to 1 meter per second. So when the water is entering the intake, the velocity should be 0.6 to 1 meter per second. It will result in two things. First is it will not lift the silt from the bottom, number one. Number two is that it will not cause any turbulence. Location, it has to be above the dead storage, of course, because if it is below the dead storage, it can capture silt plus air can go inside. And it should be sufficiently below the MDDL, because water will never go below MDDL. So you have to keep it below the MDDL. The top of intake should be below MDDL so that air can never go inside. Additionally, we have to give some extra margin, some extra buffer, because if the water is flowing inside going inside the bell mouth, and if it is very close to the MDDL, then what will happen when the water is coming down, when water is coming down to the MDDL, what will happen? Vortex will form, and that vortex will result in the entry of air inside the tunnel. That's why it has to be kept sufficiently below the MDDL. Trash rack, what is trash rack? It is a screen kind of, which is provided at the entrance of intake to prevent the entry of any trash which would not pass through the small opening in the machine, especially in the turbine and the governors. The flow through velocity should be 0.6 to 0.9 meter per second. Spacing of bar should be less than the opening between turbine. Of course, that's the thing, because you know everything which can pass through the trash rack should be able to pass through the blades. So the opening in the tracer should be less than the opening in the blades. And piers and reeds should be streamlined to reduce the turbulence. Next, desilting basins. Desilting basin are arrangements which are desilting basin or desilting chambers. These are the arrangements which are provided to reduce the silt, to remove the silt and take it back to the river. This is a desilting chamber. This is a desilting basin. Here, the bottom of this desilting basin is also kind of hopper shaped. To the bottom of this desilting basin is also kind of hopper to capture this silt and take it out from the desilting chamber. And these desilting chambers are very large. If you can see, there are two workers standing here. So you can imagine the height. Okay, this is the tunnel, silt flushing tunnel at the bottom. So all the silt which is settling down will come here, slide through this, collect here, and will be taken out of the desilting basin. The clear water will go out from the desilting basin from the top. Its purpose is to remove the suspended silt from the water and to prevent so as to prevent the damaging effect on the turbine. The scouring of the turbine will be prevented. It is designed to settle the particles of size which are larger than a particular size, and generally that particular size is 0.2 mm. So most of the desilting basins are designed to settle the particles of size greater than or equal to 0.2 mm, and it is generally used provided just downstream of the intakes. Water conductor system, it's an entire system which is used for carrying the water from desilting basin or intake to the powerhouse or the surge shaft. So water conductor system's purpose is to carry the water from desilting basin to the surge tank. You can have channels or you can have tunnels. The channels can be rectangular. You can also have trapezoidal. Trapezoidal are preferred for large ships. For small channels, you can also go for rectangular. And tunnels can be circular, D-shape, horseshoe, modified horseshoe, or so on. It can be square also for very small tunnels. Tunnel design, there are two aspects, hydraulic design and the structural design. The hydraulic design means what should be the diameter, what should be the shape and so on. And structural design means what should be the percentage of steel, what should be the thickness of lining and so on. So hydraulic design means the pressure flow velocity should not be excessive. Otherwise what will happen, scoring will take place. Generally in case of concrete tunnels, concrete line tunnels, we provide maximum 5 meter per second. And in case of steel line, we can go for high, but generally we don't go for more than 7 meters per second. And roof of tunnel should always be below the energy gradient, because if the hydraulic gradient line is below the roof of tunnel, the vacuum will generate and that vacuum will create bubbles. And when those bubbles are collapsed, it will cause cavitation in the surrounding concrete or the steel. So the roof of the tunnel should always be below the hydraulic gradient line, maximum energy line. The structural design means the rock surrounding the tunnel should be stable. It should not collapse. It should not be, there should not be excessive dilation. There should not be excessive settlements or so on. And this entire tunnel has to be supported by itself using rock bolts, by using shotcretes, by using grouting, steel ribs, lattice girders. These are all technical terms that I'm telling that will be discussed in more advanced lectures. But yes, this entire tunnel should be stable. If you have to give a concrete lining, then how much should be the thickness of lining, whether it should be RCC or PCC. If it is RCC, then what should be the reinforcement diameter, spacing, and so on. This is the structural design. Surge tank. Surge tanks are again a very large component in run of the river schemes. And if you see, this is a photograph that I clicked for Pune Sancho 2 hydropower project, and you can see the workers standing here and the entire excavator which is sitting here. So it's a surge tank of 35 meter diameter, and it was around 130 meter deep. Surge tanks are used to relieve the water hammer forces, and it is also used for pressure regulation and flow regulation. And if you can regulate the pressure and flow, you will obviously be able to uh, regulate the machine speeds. And of course, the main purpose of any hydropower project is to generate electricity at 50 hertz, because the frequency of electricity in power frequency of AC current in the grid is 50 hertz. So that hydropower project should generate electricity at 50 hertz so that it matches with the grid. And to achieve this 50 hertz, the speed of machine should also be in sync at 50 hertz. So that's why you have to so that is why you have to regulate the speed of machine, and that is why you need to regulate the flow and pressure. And to regulate the pressure, you will have to relieve the water hammer. That's why you need a pressure chart. Two aspects of design: hydraulic and the structural. Hydraulic means what should be the shape, what should be the size, what should be the height, what should be the top, what should be the bottom. It should be able to cater during the fluctuation of water and pressure. It should be able to take all those fluctuations. The height of the top of the surge tank should be at least 1.5 meter above the maximum upsurge, the maximum water level, and should be at least 2 meter below the lowest water level which is going to take place in the surge tank. And it should also be sure that there is no vortex formation at the bottom of the means the surge tank. If you study, there will be, of course there will be different lecture on that. If you study a surge tank, there is generally a orifice which is provided at the bottom. So when a water is entering the orifice, there is a possibility of vortex formation, and that vortex should not form. And that is why generally we have a higher buffer at the bottom as compared to a buffer at the top. Structural design means it should be, it should not collapse. The rock around surrounding the surge shaft should be competent. Plus, lateral rock cover has to be provided, because internal pressure will be distributed in the side rocks. And if you don't have a sufficient lateral rock cover, it may fail. It should be designed for internal water pressure, which will generate hoop stress, and also the external loads, including the front pressure, means the pore water pressure. It is not designed for the lining is not designed, the if you are providing a lining, it is not designed for the rock load. For rock load, you have to provide rock bolts the and the short rake or ribs. Talking about penstocks or pressure shaft, as I said previously, if it is on surface, it is a penstock. If it is underground, then it is pressure shaft. In this case, we can see it is on surface, on the ground, so it is a penstock. It is used to transfer the water from the surge tank to the powerhouse. The penstocks are designed to resist the total internal pressure consisting of static plus water hammer. So the worst case, if you are designing for the worst case, means the static water pressure plus the water hammer, it will always be safe for static minus water hammer pressure. Okay. If it is subjected to outside pressure, like if it is underground, and say for maintenance purpose, the pressure shaft is emptied. In that case, there is some external water pressure, pore water pressure, which is acting on the top. So it should not buckle under that external pressure. For that also, we have to check the thickness. We also have to design some penstock specials, like a bifurcation piece, means where one pipe is divided in two, that is a bifurcation piece. Trifaction piece, where one pipe is divided in three parts, that is a trifaction piece. Bends, when the direction changes. Expansion joints, reducers. Expansion means where diameter is increasing. Reducer means where the diameter is reducing. And thrust collars, where the water hammer, the force due to water hammer is transferred to the surrounding rock or to the ground foundation. And there are many other penstock specials like expansion joints and so on. This is a typical layout. So if you can see, there are two options. This is the surge tank, this is the turbine. So either you can go like a vertical pressure shaft and then a powerhouse and then the TRT, or you can go like This is a part of pressure shaft. Then uh, on surface it is a penstock, and again there is a pressure shaft, and then it is meeting the powerhouse, surface powerhouse. In this case, it is a underground powerhouse. Powerhouse. It houses all the machinery and turbines and generators and everything which are used to generate the electricity. So this is a typical layout or drawing, I would say, a diagram. Here is the pressure shaft which is meeting. Generally here you have a inlet valve. It is called as main inlet valve. It's a butterfly valve. And then there is a spiral case, scroll case or a spiral case. That spiral case, the scroll case is, the purpose of that scroll case is to evenly distribute the water inside to the turbine. Okay, that goes to the turbine. The turbine is, then water goes from turbine to the draft tube and goes out. When the turbine is rotating, it rotates the shaft, the coupling, and in turn the rotor. And outside the rotor there is a stator. By rotating that coil inside a magnetic field, you generate electricity. Generally, that electricity is low volt and high ampere. It is then taken to the transformer hall where it is converted to high volt, low ampere. Power remains same, except the some losses during the transmission. The powerhouse houses all the generators and appurtenant machinery. The components of a powerhouse are the machine hall, where the machines are installed, a service bay, which is used, that space of machine service bay is used to for maintenance and repairing of the components. Auxiliary bay or a control bay, which houses all the equipments for control of the entire powerhouse. Substructure and superstructure. Substructure means everything which is below the normal soil level, and superstructure means everything which is above the normal soil level. Design of powerhouse, you will have to design for gantry loads, for external loads, for machine loads, for earthquake loads, and so on. And turbines can be impulse or reaction or gravity turbine. I am not going to the detail of this. These are a different topic altogether. But yes, I will give you a small guideline about impulse turbines are used for high head, low discharge. Reaction turbines are used for low head, high discharge, and gravity turbines are other kind of turbines. You can also have kind of bulb turbine or some kind of reversible turbines which are used for pump storage schemes. So this Pelton wheel is a reaction turbine which is used for high head and low discharge. This is a Francis turbine which is used for low head and high discharge. And finally, you have a bulb turbine. This is a chart which shows it's a kind of guiding chart for the choice of turbines. Uh, it shows the suitability of turbine, a type of turbine for flow in meter cube per second, cubic meter per second, and the head in meters. So I'm going to give you just 2 minutes. Pause this video after I ask the question. Think yourself and then see the answer. So answer will be just following the video, but I request you to pause the video for a minute. So I'm going to ask the questions. If you see the flow is 5 cubic meter per second, so here is the line, and say the head is slightly above 50, let me say 52 or 55 cubic meter per second. The line is coming like this, and the point of interest is this. Okay, now which turbine will you select? Turbo turbine, black dotted line; Francis turbine, the red line; Kaplan turbine, the blue line. These two, Archimedes and crossflow, are out of this zone. So pause this video for just 1 minute. Think on it. Think of the answer, whether you will go for turbo, Francis, or Kaplan, and then resume this video. So I will tell you the answer. The choice for this should be Francis, because you see, for turbo it's on the boundary, it's the edge. For Kaplan also it's on the boundary, again it's the edge. So although you can design a turbine for this, but it will not be as efficient as Francis. because this point of concentration is in this almost in the center of this red polygon. So in this case, you should go for Francis turbine. Surface powerhouse. These are typical components of a surface powerhouse. You have this, just a second. You have this reservoir, and from reservoir directly the penstock is coming, and no desilting basin, because generally the storage scheme, in case of storage scheme, you have large reservoir, so silting takes place at the upstream of reservoir, and generally you have clear water. So directly there is a intake, and intake there is a penstock directly meets the turbines, scroll case, a draft tube, and it exits to the tail race pool. Then there are stator rotors, a gantry crane, complete machine hall, and then you can have the arrestor or the switch yard on the top of the hall or on the switch yard on the side on the land. There are gates. This gantry crane is for lowering the stop lock gates. You have to provide some transformers to step up the voltage to lower down the ampere, and so on. So these are the typical components of a surface powerhouse. Finally, the tail race system. So once the electricity is generated, it is given. The water has to be given back to the river. It has to be transported back, and that is done by tail race system. It can consist of a channel, or it can be a tunnel, or it can be directly the water can be given directly from the turbine to the river, like this in case of surface. So if you see, there are some components visible here. This is the upstream surge tank. This is a powerhouse. Here is the turbine units, and immediately after turbine, you have the tail race outfall. This is the machine hall, and nearby this machine hall, you have the switch yard, okay, and transformers. Tail race system is the last part of the water conductor system. Minimum tail water level is critical for the design of turbines, because you have to have some minimum tail water level for the design of turbines, because generally in case of Francis turbine, the entire system is pressurized. So you have to have some minimum tail water level, tail water pool at the end. Usually the tail water pool has to be provided by creating a small weir after the water is taken out from the system, and downstream surge tank may be required or may not be required depending on the length of the TRT. So, thank you very much for your patient listening. I hope I was able to clear the concepts of the hydropower plant, how plants are designed, what are the different components, what are different the design aspects, what are the different criteria which have to be checked, and so on. So thank you very much. I'll just give you my contact details so that you will be able to contact me if required. So I'm writing my details here. You can call me, you can drop me a message, or you can contact me through mail. Okay, these are my contact details. You are free to contact me whenever you like, for any queries or for any suggestions, or even for if you face any difficulties uh, in your office. You can contact me anytime. So thank you very much, guys. Stay safe, stay healthy, and I hope you will be using this knowledge in your office. Thank you very much.